Last presentation for today is by another one of ETH, Theodoros Theodoridis, or as we know him with slightly removed redundancy, as Theo. He's currently a PhD student here at ETH. He works on general purpose compiler and how to optimize the performance they can obtain. He just won with his work the ASPLOS Best Paper Award. So that's really nice work, and today he will tell us how he will eventually build the perfect compiler. Please.
Thank you. So, yes, as the title suggests, and as Marcus also mentioned, this will be a talk on compilers, and we won't really go into how we will build this perfect compiler. Rather, I will just tease two of our recent works towards this direction and our general vision. But before I do that, let's look at a very high-level overview of the anatomy of an optimizing compiler. So the simple task that a compiler has to solve is to just translate some kind of program from some kind of source language into some target. And this typically is assembly code, but it can be any number of things. And what we also want from a compiler is to optimize this piece of code or this program. And the way it does this is by applying a series of transformations, either to individual parts of the program or to the whole program itself. But a compiler cannot just blindly do this. It has to understand the code a bit. There are analyses that, for example, are used to figure out whether a certain transformation is even legal to apply. And there's a certain interplay between these. The better we can analyze a piece of code, the better we can optimize it, and the better we can transform it. But the more we transform a piece of code, the more we are affecting these analysis results. And in fact, the compiler has to rely on dozens of these simple individual analysis or transformations. And this creates a bit of complexity. Even simple changes in one of these elements can have very cascading effects that affect the behaviors of a lot of others, and in turn they can affect quite a lot the quality of the output of the compiler. And to make matters even worse, a lot of these like small boxes have to make decisions. For example, should a certain function be inlined or should it not? And these are driven by heuristics. And these heuristics typically are crafted by compiler engineers that either tune this so that the compiler performs good in certain benchmarks or the applications that their employer cares about. So the question is, we have this really complex system with a lot of unpredictable behaviors, and how well does it do? How far is it from a perfect compiler? Well, the obvious answer is that it's pretty far from it. And there are a lot of example works that demonstrate this, and not only in terms of the quality of the compilation, but also in the tooling that we have access to. And one such example is Bolt, binary optimizer. So this runs after the compiler, and it performs very simple transformation, nothing like the fancy stuff that an actual compiler would do. And it was, if you use Bolt to actually optimize one such compiler, LLVM, you can get a compiler that is 30% faster. And I don't know when was the last time that you looked at a compiler research papers, but the numbers that they usually report are speedups of the like 5%, 2%, 3%, sometimes 10%, but we rarely see stuff like 30%. And in the tooling side as well, here's another example, Bolt. Not Bolt, Mold. A new linker that improved upon the state of the art with up to 5x. So there's clearly a lot of room for improvement in both the compilers and how we actually research compilers, and at least from the side of performance or optimizations. And our approach is slightly different. We don't want to just pick some of these components and improve it. But what we want is to understand, what is the gap? How much better can a compiler get? So we actually say we focus on this red component, and we ask the question, what would happen if we had an optimal version of it? What would happen if we had, for example, perfect analysis results, or a heuristic that always makes the best decision? How far are we from this, or what would be the gain in having access to this? And there are just two steps in answering this question. First, we need to find the optimum. And that's the difficult part, because a lot of the search spaces that a lot of these heuristics navigate are humongous. There's just no way to naively enumerate all possible choices and find the best. And also the way that compilers have been designed up to now doesn't really allow us to do this, because they don't give us access to the right information that we would need to answer this question. Therefore, we also need to build tooling to support this kind of quests. And, well, the second step is that if we had access to the optimum, we would just compare it with what the compiler is doing, and then we can establish some gap. We can establish what is the gain of spending research efforts and engineering into that component, instead of just blindly trying to improve things left and right by tuning magic constants in a compiler. And this is exactly what we did in our two recent pieces of work that I will present, or tease. I will not go into many details simply because I don't have a lot of time. And one of them was in the problem of inlining. So the question that we try to answer is, what if we had the perfect inliner? And before I explain the main idea or the key takeaways, I'll briefly remind you what inlining is. It's a compiler transformation that just replaces function calls, such as the call to bar down there, with the bodies of the function. So in this case, it would look something like this. A compiler would not do this at the source code level. This would be done in some kind of intermediate representation, but I'm just showing this because it's easier to understand. So the reason that we want to inline code, or that the compiler wants to inline code, is because a lot of its analysis and transformations operate on intra-procedural level, so they only operate within functions. And by inlining code, we make the job of the compiler much easier, because now it has access to a lot more context. And therefore, here it could very easily determine that the condition in this if statement is always false. And it can just throw away the remaining code, and it can further simplify this function into just return x. But clearly, inlining is very beneficial, but the problem is that we cannot just blindly inline everything, because this can have negative effects. For example, here's a very simple call graph that represents a program, so the nodes are just functions and the edges are the function calls. And the compiler that we were testing actually decided to inline this with the bold ones, the red or orange ones. And what we asked the compiler was to try to minimize the program size. And by inlining these calls, it actually increased the program size by 70%. So it was too aggressive. On the other hand, if the compiler decides to do the right thing, or a slightly better job, then it can actually improve things quite a bit. So here we see the effect of enabling and disabling inlining on program size for the popular benchmarks with Spec 2017. And what we see is that by taking the right decisions, we can actually improve or reduce the program size, the binary size of the benchmark, by up to 3x. So in this work, we focused on optimal inlining for program size, but if we had a similar plot for performance, we would also see benefits because of inlining for the reasons that I just explained. So clearly, inlining is a very important transformation, and the way compilers decide what to inline is through these heuristics. And these are, again, heuristics tuned by engineers with a lot of magic constants that keep being updated as the compiler evolves. But the question that we try to answer is, how far are these from the optimal? And in this case, the optimal is the set of choices that lead to the smallest possible binary size. And the difficulty with answering this question is the very nature of the problem. So if we have a program with n calls, we have 2 to the n different combinations that we can try. So we cannot just exhaustively try everything and pick the best. So in the case of Spec 2017, if we actually try to do this, the number of times that we would need to run the compiler is several hundreds of magnitude larger than numbers such as the number of atoms in the universe. So clearly we cannot do such a thing. But what we argue, or what we show in our work in this paper, is that this number is quite pessimistic. We can actually prune this search space drastically by a lot, to the point that we can go from this number of atoms in the universe size down to something that we can exhaustively search in a single machine, or in a single beefy machine, in a couple of days. We still cannot handle all of Spec, because there are also files there that are auto-generated, and just compiling them takes minutes. But we can handle a large part of it. And having access to this reduced search space, we can find the optimal configuration for all of these. And then we can start answering questions such as, what is the gap? What is the cost that we are paying because we don't have access to the optimal and we are using a heuristic? And as this plot shows, for around half the cases, LLVM is already finding the optimal. So it's a very well-tuned heuristic. But on the other hand, there are several cases where it doesn't. And in fact, the maximum difference is around, or the maximum size overhead is around 300%. And here we are really asking the compiler to minimize this, the program size. But we don't just have access to this gap. So what is the between the optimum and the heuristic? We also have access to the actual decision, the inlining choices that led to this. So we can start answering questions such as, how often does the heuristic agree with this optimal strategy? And what we can see, for example, is that in most cases they actually agree. They either both inline or they don't, or they both do not inline. But on the other hand, the heuristic tends to be quite aggressive, and this leads to this overhead that I just showed in the other plot. And we are able to answer these questions and understand the problem a bit better because we had access to this reduced search space, because we were able to prune it in a level that can be exhaustively searched. And the details on how we did this are actually in the paper. I don't have time to go through this. But the main idea is this one. Given a problem with what was considered up to now infeasible to exhaustively enumerate, we found a way to do this. And this is one of what we believe is the key strategies to understanding larger parts of optimizing compilers. So in the second piece of work that we did, we also tried to do something similar where we compared another compiler component against a theoretical optimal compiler that obviously doesn't exist. But at the same time, what we developed was a method not only for doing this comparison, but also finding through interactions of other compiler components with this one, the dead code elimination, we're able to find problems in a number of other such analysis and transformations. So we can find a number of missed optimizations that the compiler is simply failing to apply for one reason or another. And to give you an example of what I mean by that, let's look at this simple piece of code. So what we have here is essentially a simple function, just main, and a global integer initialized in 0. And what this program does is, first we check, is this non-zero? In that case, we return 1, else we write 1 to it and return 0. So this is a very trivial program that is, you would expect that no compiler would struggle with this. And what happens is that at the point where we have this check, A can only ever be 0. So this whole if statement is dead code. This program can never return 1. And also this write to A is a dead store in the sense that we never read A again, so the compiler doesn't need to generate code. So what you would expect is that the state-of-the-art compiler would generate something like this, essentially return 0. But if we use GCC or LLVM, so essentially the most used compilers in the industry nowadays, or that probably have compiled the most code in all of history, we see this. So we actually, at the highest optimization level, they completely fail at that. They don't optimize the if statement, they don't optimize the return one, they generate code for the dead store to A, and they're really failing at that. Now, the reason is that because certain data flow analyses are not flow sensitive in these two, but the fact is that one can find a lot of such problems, not just related to data flow analysis, but a number of other components. And the way we can actually find this can sound a bit unintuitive, but it's by looking at dead code elimination. So DC is another transformation pass that essentially removes code that either can never be executed, so like the body of the if statement, or code whose execution doesn't really affect the program's behavior. So like the dead store. We wrote some value to some piece of memory that we never read again, so it's dead. And the reason that we can use this to infer that something else has gone wrong is the fact that whenever we remove a piece of code from our program, we make it simpler. And simpler programs are easier to analyze and easier to optimize. So whatever runs after DCE, a number of other transformations, can potentially have an easier task at doing whatever their job is. At the same time, DC will be run multiple times because the compiler tries to do this again and again. And these will also affect how well a compiler can eliminate dead code. And there are also things that run before it that also affect how it's... what we end up with is a component in the sort of in the middle of the compiler that interacts with a lot of others. So, and what we can do now is we can infer the following. If for whatever reason a compiler fails to eliminate a piece of dead code, this, not necessarily, but this might be an indication that something else has failed. And this is exactly how we can find, or how we have found, a number of missed optimizations in components that you would really not expect to be relevant to dead code elimination. Things such as auto-vectorization, or various analysis, or loop transformations, or even simple stuff like constant propagation that should work most of the time. And now the difficulty here is that the compiler doesn't really tell us what it failed to dead code eliminate, because the compiler doesn't know what it failed to dead code eliminate. So, yeah, anyway, what I was trying to say and lost my train of thought was that what we had to do in our piece of work is to actually develop a way of figuring out what has not been dead code eliminated. And again, the details of that, there's no time to go into this, but these are on the paper. And having access to such a tooling that can tell us what parts of a program have been missed by the compilers, what dead parts, we can start answering questions such as, how good are compilers at DCE? How good are compared to a theoretical compiler that would eliminate everything? And to answer this question, we look at a corpus of 10,000 test programs. These were randomly generated by CSmith. And we could measure that the amount of dead blocks in these programs was around 3 million. And now we can compare this to, and our theoretical perfect compiler would eliminate all of these. But now we can compare this with real compilers, such as GCC and LLVM at various optimization levels. And as we observe, even at the highest optimization level, they miss around 5% of these. And at first you might think that, well, this is an amazing result. They are 5% away from what is theoretically possible. Or 5% away from the optimum, at least in this setting. But it is exactly this 5% that can let us get some insight in what is going wrong in the rest of the compilation pipeline and find all of these other issues, such as in vectorization, in peephole optimizations, and so on. So, and this is essentially our view into the compilation or in the problems, in the missed optimization in the compiler. And it is important to find such missed optimizations, not only to understand the capabilities and the limitations of a compiler, but also because we want to improve them. We want to report such problems to compiler developers. And we have developed tooling that can do this fully automatically. So you just run the tool and then it finds such small examples that can demonstrate the issues in the compiler. And we reported around 100 of these, both in GCC and LLVM. And up to now, around a third have been fixed. But this is just the tip of the iceberg, because if we start also analyzing older compiler versions, for example, for regressions that haven't been fixed yet, we can find several hundreds of these. But we just didn't want to annoy the developers and start flooding their bug trackers with all the ways that their compilers are broken. So, and now how we find this and how we turn this using DC to a fully automated tool that can find these issues are, again, the details are in the paper. Yep?
I had a question. So one question I have is that, is the compiler incorrect? Like there's an error in the compiler? It's not as if it's producing unsound code. Sometimes it's sound. But is it something like this? Or is like an easy patch in the compiler? Or it's a more fundamental rewrite, and many of these things are a side effect of this more fundamental rewrite. So these are like 15 rewrites, or one rewrite to make 15 fixes.
So these were 15 separate fixes. So some of some of the reports were duplicates, so a single rewrite fixed more than one. Okay. But these are individual reports or separate issues. Now, we are not testing whether a compiler is sound. We are assuming that it is sound, which obviously is not true. But some of these issues that we reported, such as this one, require a lot of work to fix, and they haven't been fixed because they need to do a lot of rework in the compiler. Others were quite obvious, like somebody implemented people optimizations and forgot some edge case. And others were, yeah, a bit triggered a lot of discussions in the developers on how they can handle even more complex cases. Yes?
So tail code elimination is always a good optimization because most of the time it is profitable. But lots of optimizations deal with the cost model too. So have you looked at cases where we miss the optimization but it's because for a good reason for the cost model?
So, as you said, dead code elimination is always good with an asterisk because, as I said, this is a really complex system, and what can happen is that because you didn't dead code eliminate some code, then the final code alignments was slightly different, and then it would have been better to not dead code eliminate. But anyway, compilers don't consider that.
A lot of other optimizations that's a lot worse.
Yeah, exactly. So we had a few cases where it was simply because the compiler decided not to inline a function and therefore it couldn't dead code eliminate. But a lot of these are also obvious cases where the compiler should have done that. Because, for example, the analysis was not, didn't consider some edge case that should have considered without being detrimental or without involving any decision. So, and again, the details on this there are more details on that in the paper. So, and to recap, so our vision or our approach is that what we believe in order to significantly advance compilers, we actually need to start understanding them. We need to measure things. We need to know what is the gap instead of just blindly improving individual components and hoping that things would be good. But this is at the start of our quest. So with these two pieces of work, we only looked at two components and a few interactions between them. But there's a lot of other things to study. There are several analyses, there are heuristics, there are transformations that are still very poorly understood, and also the interactions between them. And currently in our lab, we have some or a lot of ongoing work towards this direction. And a few examples are the following. So what if we had optimal alias analysis? What if we had a way to derive this perfect information? Would the compiler actually benefit from that? Would it perform better? Would it perform worse? Does it even make sense in the context of the current compilers to spend research and development efforts into improving alias analysis, or should we be improving how the compilers are using this information? Another project is optimal pass pipelines. So this has been an open problem for the last 30, 40 years. So in the sense, how do we actually schedule these transformations? How does the compiler decide which and how many of these to apply? And what we are looking at is, similarly to our inlining work, is how can we prune this search space to do better than what the compiler is doing right now, or even adapt a compiler to a specific code base that is of interest to us. And lastly, for example, how can we improve the compilers? So in our inlining work, we are now in the position that we can essentially generate infinite amount of data that contain call graphs with our optimal inlining strategies. So can we actually use this to improve current heuristics or even learn a new heuristic based on these to improve upon the state of the art? And there are also many other similar directions that we are looking at along this quest towards the perfect compiler. And I think I can now take your questions.
Arrows in this work, introduce optimal outlining of functions, because, for example, folks at PlayStation and like game engine companies, they want to target code size. So yeah, again, this came to my mind because I watched like a talk from PlayStation folks at some LLVM forum.
Great question. So, in a way, outlining and inlining are the same problem.
Yeah.
Or a different view or the two sides of the same problem. So we haven't looked into this, but I mean, if you think about it, the inlining, like the way we structure code is completely artificial. There's no reason why function boundaries are where they are. It's just some developer decided to write their code the way they did. So we haven't looked into this, but it's a much more complex problem. But I think that at some point in the future, we need to not even look at it from the other side, but just look at the combined problem, because it really makes sense.
So I had a quick question, like not in the LLVM GCC lands, but more in the JIT. Did you look at like dynamic compilation also? And also in the, are you thinking about this? And also in the machine learning space, like the PyTorch and other settings?
We didn't, and I think the problem, or some things are nicer in the dynamic world because we have a lot of additional information that a head of compiler doesn't. But on the other hand, it's a bit more messy to do these experiments, and I think one would have to deal with a lot of pain into kind of having stable environments and so on. But we didn't do this at all, so we didn't look into that. But what do you mean about the PyTorch in the PyTorch world?
Like let's say the TensorFlow compiler doing all kinds of optimizations. And so, yeah.
So I think one interesting kind of parallel to our inlining world that you have you would have in PyTorch or TensorFlow or other similar frameworks is there they have the problem of kernel fusion. They need to decide what to fuse and what to not. And I think similar techniques to what we did with our inlining would make sense in that space. But oops, we didn't look into that.
Oh, okay, so thanks.
Other questions? Okay.
So in some sense, lot of modern compilers like GCC LLVM is like hopeless because they have all these crazy heuristics. Can you do something meta to say some of these things are because it happens in a certain reason, or so you can improve that and find one after another?
I'm not sure I understood
So
the question.
you can say this is all because of pattern matching heuristics, or this is because the analysis failed or something. Are there like some higher level learning that might applicable than like just the whack-a-mole every one at a time?
So to go back to your before I try to answer this, to go back to the hopelessness of the situation, I think one reason that these compilers have become so complex is the very fact that we don't know how to navigate the optimizations and problems that they are solving. So instead of kind of figuring out, I should rerun this optimization after doing this, developers have just introduced more peephole optimizations or new optimizations that are just sitting somewhere in the compilation pipeline, and you can even read comments in the source code of the compilers. Why do we do this here? We should probably investigate who did this and why. And so to answer or to comment on the second part, I think in many cases the answers are obvious in the sense that you can see that the compiler just didn't inline something that it should have inlined. But the problem is that in some other cases, you have very complex interactions between your passes. And so, for example, maybe because you didn't dead code eliminate something ended up after its register allocation being done wrong because you had an extra live range that did not exist before. And debugging this is, I'm not sure how easy that would be, or without any manual effort or reasoning about that.
My thing is, I think debugging things that are broken is much harder. It might be interesting whether this will give you a new direction to do some of them from scratch. If you can say, look, this is what all these people are doing. So don't do this in inlining. Don't do all this crazy thing. Here might be easy, because this is what everybody is missing. If you get a little bit of higher level and kind of understanding, here are all the kind of problems we are having. So, okay, think differently.
Yeah, sure. And I think another maybe kind of similar direction would be how do we take this monstrosity and simplify it and get something that is in most cases equivalent, so it doesn't have special cases for every single possible input source code. But also building a compiler is kind of a huge task, and I think here we have the same issue as in people that do operating systems. We cannot build the whole thing from scratch and expect that it will perform similar to LLVM or GCC, at least with not a lot of effort.
If I actually may add a question on this, because it was not clear to me in this line of work. If you talked about the interaction of the transformation with other transformations, right? And let's say you find some of your bugs, which are sort of performance optimization bugs, and you just say, look, here it could have been a lot better in whatever metric if before that, let's say 2 passes had been done in an opposite order. I mean, what are you going to do by this? Because if you then change the order, you fix your one example, but there's 1 trillion other pieces of code that may suffer from this, and you will not be able to even assess whether you get a benefit. So how do you handle if there's a dependency like this? Do you give up or you have a trick?
I think the real solution is to not have a fixed order. So right now, what both of these compilers do is they have the fixed order that somebody or a lot of people collectively decided on. And we know that this is not a good order. Yeah. We know that we can come up with a lot of examples that show that this is bad. Okay. But so what we would need in the end is a compiler that adapts. Okay. Maybe I need to run it over the weekend to figure out how to a good order. But this fixed model obviously doesn't work.
Okay, but that is also known as a holy grail problem, phase ordering.
Yeah,
it's studied for decades, right? Including machine learning tools people have tried. So there you get immediately to the holy grail problem. Right? And anyway, but there was one more question from you, maybe, or you're good?
No.
Okay. One last question, if anybody wants. Okay, good. Then thanks again, Theo. Nice talk.